For as long as humans have watched the sky, the moon has shown us a single, unchanging face. The dark blotches we call the man in the moon, the bright highlands between them, these features never shift. Night after night, century after century, the same hemisphere stares back at Earth. This is not coincidence. It is a result of a slow gravitational bargain called tidal locking, a process billions of years in the making. Earth's gravity gradually stretched the moon, dragging on its rotation until the spin period matched the orbital period exactly. Today the moon turns once on its axis in the same 27.3 days it takes to circle our planet. The consequence is precise and permanent. One side always faces us, and one side never does. Ancient astronomers had no way to see the missing hemisphere. Aristotle, Ptolemy, and the great observers of Islamic and Chinese traditions all studied a moon that kept half of itself hidden. Even Galileo, turning his telescope skyward in 1609 and sketching craters and shadows, could only refine the near side. The far side remained pure imagination. Over the centuries, curiosity hardened into obsession. Writers speculated about what lay beyond the visible edge. Hidden cities, alien seas, a mirror of the familiar landscape. Scientists reasoned more cautiously but had nothing to test their guesses against. A slight wobble in the moon's motion, called libration, let observers peek at roughly 59% of the surface over time, but a full 41% stayed absolutely beyond reach. No instrument on Earth could ever change that. The only solution was to leave Earth entirely, to send a machine around the moon and photograph what human eyes had never witnessed. Through the first half of the 20th century, that remained impossible. Rockets could barely reach the upper atmosphere, let alone escape Earth's gravity and navigate to lunar distance. Then the space age arrived with startling speed. By 1957, the Soviet Union had orbited Sputnik. Within 2 more years, engineers in Moscow were preparing something audacious, a spacecraft designed to fly behind the moon and turn its camera on the forbidden face. In October 1959, humanity was about to see the unseen. On October 4, 1959, exactly 2 years after Sputnik, the Soviet Union launched Luna 3 atop a modified R-7 rocket. The spacecraft was small, a cylinder roughly 1.3 meters long, weighing about 278 kilograms, bristling with antennas and solar cells. Its mission was unprecedented: swing around the far side of the moon and photograph a hemisphere no eye had ever seen. The trajectory was a masterpiece of celestial navigation. Luna 3 looped behind the moon, passing within about 6,200 kilometers of the lunar surface, using the moon's own gravity to bend its path. As it crossed to the far side, sunlight illuminated the hidden terrain, and the probe's cameras began their work. But this was 1959. There were no digital sensors, no memory chips. Luna 3 carried a genuinely astonishing solution: a fully automated photographic laboratory operating in deep space. The spacecraft used a dual-lens camera loaded with 35mm film, reportedly a temperature-resistant stock recovered from American reconnaissance balloons. Over roughly 40 minutes, it captured 29 photographs covering about 70% of the far side. Then came the hardest part. The film had to be developed, fixed, and dried. All on board, all automatically, all in the vacuum and radiation of space. A small chemical processing unit carried out each step, transforming exposed film into finished negatives inside the orbiting machine. Once developed, the images were scanned by a light beam and a photomultiplier, converting the pictures into electrical signals suitable for radio transmission. The engineering margins were brutal. The spacecraft had no way to stabilize perfectly. It spun to hold its orientation. Power was limited, communications fragile. On its return leg toward Earth, Luna 3 finally came close enough to transmit. The first attempts, from great distance, produced almost unreadable noise. Only as the probe approached did clearer signals arrive, line by painstaking line, decoded at Soviet tracking stations. What emerged onto photographic paper was crude by any modern standard, smeared, low in contrast, scarred by interference. Yet these blurred frames represented one of the great firsts in exploration history. For the first time, human beings held images of a place that had been invisible since the dawn of our species. And what those grainy ghosts showed would surprise everyone. The signals reaching Soviet ground stations in mid-October 1959 arrived as faint, flickering lines. Technicians assembled them slowly, building each photograph from transmitted rows of brightness values. The results were maddeningly imperfect. Radio interference streaked the frames. Contrast was poor, resolution worse. Of the 29 images captured, only about 17 proved usable, and even those looked like ghosts, dim, smeared impressions of a distant world. Yet when scientists studied them, they saw something no human had ever seen: the geography of the moon's hidden half, and it did not match expectations. On Earth's familiar near side, the eye is drawn to broad, dark patches, the Lunar Maria, or seas, vast plains of solidified basalt covering roughly a third of that hemisphere. Observers had reasonably assumed the far side would look similar, perhaps a mirror image of the terrain they knew. The Luna 3 images shattered that assumption. The far side appeared overwhelmingly bright and rugged, dominated by pale highlands and dense with craters. The dark seas were almost entirely absent. Where the near side displayed sweeping flat plains like Mare Imbrium and Mare Tranquillitatis, the far side showed a chaotic, mountainous crust, pockmarked by impact after impact. Soviet scientists at the USSR Academy of Sciences pored over the blurry evidence. Despite the poor quality, they identified a handful of features clearly enough to name them. They christened a small dark region Mare Moscoviense, the Sea of Moscow, and a bright crater Tsiolkovsky, honoring the rocketry pioneer. In 1960, they published the first atlas of the lunar far side, a modest booklet built entirely from these degraded photographs. It was a landmark of human knowledge assembled from ghostly fragments. The scientific message was unmistakable. The moon was not symmetrical. Its two faces were fundamentally different worlds, shaped by different histories. One hemisphere was flooded with ancient lava. The other was armored in battered highland crust. The blurry images raised a question far larger than any single feature. Why? Why should one side of a single body be so unlike the other? The Maria that painted the near side were missing here almost entirely. Understanding that absence would occupy scientists for decades, and it begins with the mystery of a moon without seas. The Lunar Maria are not seas of water. They are seas of stone, vast plains of dark basalt that erupted from the moon's interior billions of years ago. When enormous impacts smashed into the young moon, they fractured the crust and excavated deep basins. Over hundreds of millions of years, molten rock welled up through those cracks, flooding the basins with lava that cooled into flat, dark surfaces. On the near side, these Maria dominate, covering about 31% of the visible hemisphere. Mare Imbrium alone spans some 100 kilometers. The far side tells a starkly different story. There, Maria cover only about 1% of the surface. The Luna 3 images had hinted at this, and everything learned since has confirmed it. Something had prevented the far side from flooding with lava the way the near side did. The magma existed. The interior heat existed. The giant impacts certainly existed. Yet the dark plains largely failed to form. Scientists confronted a genuine puzzle in planetary science, a fundamental asymmetry in a body that should, by simple physics, have evolved uniformly. Why should one hemisphere melt and flood while the other remained locked in bright, ancient highlands? Early explanations pointed toward the crust itself. If the far side crust were thicker, magma rising from below would face a longer, harder journey to reach the surface. On the near side, a thinner shell would let lava break through more easily and spread across the impact basins. This idea of crustal asymmetry, a moon with a lopsided skin, became the central clue. But in 1959, and for years afterward, no one could measure crustal thickness directly. The evidence was circumstantial, drawn from surface appearances alone. Confirming the theory would require instruments that could probe beneath the moon's face: gravity measurements, seismic data, precise topographic maps. All of that lay in the future. The Luna 3 images had opened the door, revealing that two hemispheres existed. Now the question was how they came to differ so profoundly. Before machines could answer it in full, another milestone arrived, one that would place living human beings in position to see the hidden face with their own eyes, from lunar orbit itself. In December 1968, the answer to a species-old question shifted from photographs to human vision. Apollo 8 launched on December 21st atop a Saturn V rocket, carrying astronauts Frank Borman, James Lovell, and William Anders. Their mission was audacious: the first crewed flight to leave Earth's gravity, travel 250,000 miles to the moon, and enter lunar orbit. No humans had ever traveled so far. On Christmas Eve, after a 3-day coast, Apollo 8 fired its engine and slipped into orbit around the moon. As the spacecraft passed behind the lunar body, it lost radio contact with Earth, a tense planned blackout lasting several minutes. During those passes, Borman, Lovell, and Anders became the first human beings in history to gaze directly at the far side. What Luna 3 had shown as blurry ghosts, they now saw with their own eyes. A battered, sunlit landscape rolling beneath their windows, crater upon crater, ridge upon ridge, utterly without the familiar dark seas. Their descriptions matched the science. The far side looked rugged, ancient, chaotic. Lovell remarked on its worn, war-torn appearance, a surface hammered by countless impacts. Anders compared the desolate terrain to a battlefield of sand and craters, gray and lifeless. These were not instruments reporting data. These were people breathing and watching, confirming that the moon truly wore two different faces. Then, as the spacecraft rounded the limb and Earth climbed above the lunar horizon, Anders captured one of the most famous photographs ever taken: Earthrise. A blue and white planet, small and fragile, suspended over the desolate gray moon. That single image reframed humanity's view of its own home, taken from orbit above the very hemisphere that had been hidden for all of history. The crew completed 10 orbits before firing their engine to return home, splashing down on December 27th. They had proven that humans could reach the moon, orbit it, and survive. They had also witnessed, firsthand, the extraordinary contrast between the two hemispheres. The far side was real, rugged, and profoundly different. Now the task was to map it completely, to transform fleeting human glimpses and grainy 1959 frames into precise, comprehensive charts of an entire hidden world. The grainy ghosts of Luna 3 demanded successors, and over the following decades, a procession of spacecraft transformed guesswork into geography. In 1965, the Soviet Zond 3 returned 25 photographs of the far side, sharper than anything Luna 3 had managed, capturing craters and highlands with new clarity. American lunar orbiters, launched between 1966 and 1967, circled the moon to scout Apollo landing sites, and, in the process, imaged vast stretches of the hidden hemisphere. By the end of the 1960s, cartographers could assemble their first crude charts of a world no human had ever mapped from the ground. The pace accelerated. The Soviet Zond probes, the Apollo command modules with their metric and panoramic cameras, and later the Clementine mission of 1994 layered detail upon detail. Clementine measured the moon's topography with laser altimetry, revealing the true shape of the far side's mountains and basins for the first time. Japan's Kaguya orbiter, arriving in 2007, carried high-definition cameras and returned sweeping views that made the alien terrain feel almost tangible. China's Chang'e orbiters added their own contributions, and in 2019, Chang'e 4 achieved what no mission ever had: a soft landing on the far side itself, inside Von Karman crater. But the transformation reached its peak with NASA's Lunar Reconnaissance orbiter, launched in June 2009. Circling roughly 50 kilometers above the surface, its cameras resolve features less than a meter across. Where Luna 3 had offered smeared shadows, LRO delivered crisp portraits of individual boulders, crater walls, and lava channels. Its laser altimeter fired millions of pulses, building an elevation model accurate to within a meter. The far side that had once been a blur of speculation became the most thoroughly mapped hemisphere of any world beyond Earth. Stitched together, these datasets revealed the far side in unforgiving precision, a rugged, battered expanse crowded with overlapping craters, almost entirely lacking the smooth, dark plains of the near side. The contrast that had startled scientists in 1959 was now measured, quantified, undeniable. And with these maps in hand, researchers could finally ask the deeper question: why should one hemisphere carry so much more rock than the other? The answer lay hidden beneath the surface, in the very thickness of the moon's crust. To measure it, scientists needed more than photographs. They needed gravity. In 2011, NASA launched twin spacecraft named GRAINY, Ebb and Flow, which flew in formation around the moon, tracking tiny changes in the distance between them. Where the crust thickened, gravity tugged slightly harder, altering their separation by fractions of a micron. From these whisper-thin variations, researchers reconstructed the hidden architecture of the lunar shell. The results were striking. On the near side, the crust averages around 30 to 40 kilometers thick. On the far side, it swells dramatically, reaching 60 kilometers or more in places, with some regions exceeding 80. The moon, it turned out, was lopsided, wearing a far thinner cover on the hemisphere that faces Earth. This asymmetry, mapped in detail by GRAINY, explained the puzzle that had haunted scientists since 1959. Consider what Maria actually are. The dark plains are frozen seas of basalt, molten rock that welled up from the lunar interior billions of years ago and flooded low-lying basins. For that magma to reach the surface, it had to travel through the crust. On the near side, where the shell is thin, rising lava had a shorter journey and could break through, spreading across the lowlands in sheet after sheet of basalt. On the far side, the thick crust acted like a lid, trapping the magma below. Even when great impacts gouged deep basins there, the molten rock rarely rose far enough to fill them. Why the crust should be so uneven remains debated. One leading idea suggests that Earth's heat, radiating onto the near side in the moon's molten youth, kept that hemisphere warmer and allowed its crust to form differently. Another proposes a colossal early collision that piled material onto one side. Whatever the cause, the consequence was written across the surface. A near side smoothed by volcanism, a far side sealed and preserved. Yet thickness alone cannot explain everything. To understand the far side's scarred and cratered face, we must look upward to the storm of debris that once battered the young moon. The far side wears its history as wounds. Freed from the flood of basalt that erased craters on the near side, its ancient surface preserves an almost unbroken record of bombardment. Craters overlap craters, ringed by still older craters, some 4 billion years old, each a snapshot of a violent past. Where the near side counts a few large impact scars softened by lava, the far side is a crowded battlefield of overlapping rings and shattered highlands. Dominating it all is the South Pole Aitken Basin, one of the largest and oldest known impact structures anywhere in the solar system. Stretching roughly 500 kilometers across and plunging as deep as 13 kilometers, it spans nearly a quarter of the moon's circumference. The object that carved it, perhaps hundreds of kilometers wide, struck with force enough to excavate material from far below the crust, exposing rock that normally lies hidden in the mantle. It was here, inside the basin's von Karman crater, that China's Chang'e 4 landed in January 2019, and its rover Yuta 2 began probing the ancient floor, for clues to what lies beneath. The density of far-side craters is more than a curiosity, it is a chronometer. Because lava never resurfaced most of this terrain, the impacts accumulated undisturbed, and by counting them, scientists calibrate the timeline of the early solar system. The far side records the tail end of planetary formation, the era when leftover debris still rained down on every world. Studying it, researchers read a chapter that Earth's restless geology erased long ago, when oceans and weather and shifting continents wiped away our own ancient craters. Samples matter here. Chang'e 6 in 2024 returned the first material ever collected from the far side, drawn from the edge of that vast basin. Analyzing these grains, scientists can finally anchor the crater timeline to precise dates, refining our understanding of when the bombardment peaked and faded. The far side, then, is a preserved archive, a hemisphere where thick crust and unerased impacts conspired to keep the past intact. Two forces, volcanism and cratering, shaped two utterly different faces of a single world. Now, the full picture assembles, drawn from 6 decades of exploration. Two hemispheres, bound to a single body, yet shaped by profoundly different histories. The near side we have always known, smooth, dark, patterned with the Maria that ancient astronomers imagined as seas. The far side, hidden until 1959, is rugged, pale, and cratered, a landscape that startled the scientists who first saw Lunar 3's grainy transmissions. 3 forces wrote this contrast. First, the crust. GRAIN's measurements revealed a shell far thicker on the far side, in places exceeding 80 kilometers, compared to 30 or 40 on the near side. Second, volcanism. That thick crust acted as a barrier, trapping rising magma below and preventing the basalt floods that smoothed the near side into dark plains. Third, impacts. Without those lava floods to erase them, far-side craters accumulated across 4 billion years, culminating in the immense South Pole Aitken Basin, a scar too, 500 kilometers wide. Each discovery built upon the last. Lunar 3 posed the question in 1959. Apollo 8 let human eyes confirm it in 1968. The Lunar Reconnaissance orbiter mapped it to the meter. Grail weighed the hidden crust. Chang'e 4 landed where no craft had gone, and Chang'e 6 carried far-side rock back to Earth. Piece by piece, the mystery of the grainy ghosts resolved into measured understanding. What began as blurry photographs, smeared shadows that scientists strained to interpret, has become one of the richest records of planetary evolution available to us. The far side is not merely a curiosity turned away from Earth. It is a preserved archive of the solar system's violent youth, a hemisphere where the past was sealed beneath thick crust and spared the erasing floods of lava. So when we look at those first images from October 1959 beside today's precise maps, we see more than technological progress. We see the moment humanity realized that our closest companion is not one world at all, but 2 faces of the same body, each telling a separate story written over billions of years. 1 moon, 2 ancient worlds. 1 moon, 2 ancient worlds.